In this mini lecture for Module 11, we're going to be talking about sensitivity, specificity, and efficiency. This is all with respect to diagnostic tests, which you know are medical tests performed to aid in the diagnosis of a disease. And there's always variability between people, and therefore no diagnostic test is perfectly accurate. And we would want diagnostic and screening tests to be accurate, and therefore ideally they should neither miss cases of disease, so if an individual is told that they do not have a disease but they actually do, that would give some false reassurance, nor should they falsely classify healthy people as diseased. So if there's a diagnostic test that was performed, we could think about how accurate that test is, and there are two obvious errors that can occur. One of them is to falsely classify someone as having the disease when in fact they do not. And the second case is when there's a diagnostic or screening test that can fail to identify a person who actually does have a disease. These two types of errors should actually sound familiar because the first one is analogous to a type 1 error for statistics, and the second one is analogous to a type 2 error. So when we think about a test, we're going to go through an example here. And imagine a test in which a high score above some threshold determined by previous work indicates disease, while a score less than that threshold indicates the person does not have a disease. And if we knew the truth, we could create a table that would look like this. So along the top, we have the truth, so either that they have the disease or they do not have the disease, in our two columns. And then in the two rows, it's the test score. So the first row is if they have a positive test score, and the second one is a negative. So the positive would indicate that they do have the disease, and the negative would be an indicator that they would not have the disease. But that's just the test. So if we administer a test to some people, and they have a positive test score, and they have the disease, these are true positives. So the test indicates that they have the disease, and they actually do. However, if individuals through the test were positive, but they actually did not have the disease, this would be a false positive. So this again is analogous to that type 2 error, because they're testing positive, but they actually do not have the disease. When negative test results occur, an individual can either have the disease or not. So if an individual has a negative test, and they do not have the disease, that's a true negative. It's accurately reflecting that they do not have the disease. But if there's a negative test result and they do have the disease, that's referred to as a false negative, and that's analogous to a type 2 error. And there are different ways that we can look at how accurate tests would be. So one of them is going to be sensitivity. Sensitivity is the probability that the test will correctly diagnose a case. So it's the proportion of the truly diseased people in the screened population who are identified as diseased by the screening tests. So our sensitivity is equal to the true positives, the individuals who actually have the disease, divided by the true positives and the false negatives. So we're dealing with the column of individuals who have the disease and how many of those individuals are actually being identified as being used to calculate sensitivity. For specificity, it's the probability that the test will correctly identify a non-diseased person. So now we're talking about people just in the right-hand column that do not have the disease. And it's the proportion of persons without the disease who are identified as not diseased by the test. So specificity is going to be the true negatives, so individuals who did not have the disease and tested as not having the disease, divided by the true negatives and the false positives, because those false positives actually do not have the disease as well. And we'll go through an example with numbers coming up. So here's an example with an elbow extension test used to assess whether or not an adult had a fracture. And then the truth was determined either by an X-ray or a follow-up visit approximately 10 days later. So the truth is that they either have a fracture in the left-hand column or no fracture in the right-hand column. And the test score is that they cannot fully extend their arm, so their elbow. And a positive would indicate that they had a fracture. And if they had full extension, that would be a negative test result. For individuals who could not fully extend their elbow, there were 311 that actually had a fracture and 336 that could not fully extend their elbow but still did not have a fracture. For individuals who could get full extension, 5 individuals still had a fracture and 306 were true negatives, so they had full extension and they had no fracture. So when we calculate sensitivity, it's the individuals that were true positives that were detected out of all of those individuals who actually had a fracture. So the true positives and the false negatives, which is 0.984 or 98.4%. So this is the proportion of people with fractures in the screened population who are identified as having a fracture by the extension test. When we look at specificity, so specificity now is looking at the true negatives, so the individuals who by the test had no fracture divided by all of those individuals who actually had no fracture, so the true negatives and the false positives. So this is 306 divided by 306 plus 336, which is 0.477 or 47.7%. So it's the probability that the extension test will correctly identify a person without a fracture. So that's sensitivity and specificity. We could also calculate positive predictive value, so it's the probability that a patient who tested positive actually has the disease. So when we calculate this, it's the true positives divided by all of the individuals who tested positive. So the true positives and the false positives. So this is 311 divided by 311 plus 336. So those are all the individuals who tested positive is on the denominator. And that's 48.1%. So 48.1% of the individuals who tested positive had the disease. Negative predictive value is the probability that a patient who tested negative really does not have the disease. So it's the true negatives divided by all of the individuals who were negative in the test. So it's 306 divided by 306 plus 5, which is 98.4%. And finally, we can calculate efficiency. It's the probability that the test result and the diagnosis agree. So in this case, our numerator has just the true results, so the true positives and the true negatives, and it's divided by all of the individuals that were involved in the study. So it's 311 plus 306. So again, these are the true results divided by all of the individuals who were involved in the study, which is 64.4%. So this suggests that the efficiency of this test, so doing this elbow extension, will correctly identify 64.4% of the cases.